My talk's about exactly what you said before, concurrent objects, and we're trying to define some correctness conditions for it, and we're trying to deal with multi-core architectures as well, which means dealing with some of the issues with weak memory. So this is joint work with a number of people that you can see. Lindsay's here in the audience if you've got any other questions that I can't answer. Okay, so the paper is doing a number of things. One of them is defining a framework for formalizing correctness conditions for concurrent objects. Then we show that some of the well-known conditions, for example, sequential consistency, linearizability, and quiescent consistency, can all be defined in terms of this framework. Then we sort of extend this to weak memory, in particular the TSO memory model, and we show that some of those can be formalized as well. And finally, we sort of have a number of applications, and that's all in the paper. So we show that some version of the Chase Lev work-stealing deque is not linearizable, but it satisfies this other condition called flush consistency, and we develop a correctness hierarchy and various other things, which I'll get to in the talk itself. Yeah, but if some of those things are unfamiliar, hopefully I can explain that. Okay, so the point of departure for us are these things called concurrent objects, and you can sort of think of them as being able to manage somehow thread synchronization on behalf of multi-threaded clients. So you'd normally, the way you'd use them is you'd instantiate them in a multi-threaded client, and you invoke its operations. And you can do many things at the same time. So what we'll assume is that each client thread calls at most one operation at a time, but different client threads may execute operations concurrently. So here's an example of a concurrent queue. It's just like a normal queue, but you've got things overlapping. So time sort of moving from left to right here. And so the different threads are sort of executing different operations concurrently. Okay, so how do we judge correctness of a concurrent object? Well, what we do is observe the concurrent history of events of the object. These are the sort of things that are happening at the interface of the object. And then we assume that the operation takes effect at some atomic step and show that the order of effects somehow corresponds to a valid sequential history. And so correctness criteria basically restrict how and when effects may take place. Okay? So here's linearizability. It's one of the most popular and well-used correctness conditions, and it says that the effect must somehow take place within the operation's invocation and response, so sometime within the execution of the operation. And if I've marked by x's the linearization points, and if I map it up to some sequential history, then I get a valid execution of a queue. Yeah, so the first thing that happens is a deque, and it returns empty, and that's valid. And the enqueues and deques from then on sort of occur in a first in, first out order. Yeah. So there are many different correctness criteria in the literature, and this list sort of keeps on growing year on year. And we sort of need to need a framework to somehow capture and think about what these the relationships between these different correctness criteria. Okay, so the framework we've developed is fairly simple. We've got histories, which are sequences of events, and this thing, which is a mapping function, basically relates the concurrent history to some abstract sequential history. And I'll just show you this by example. I'm not giving you any of the formal stuff. Okay, so here's linearizability, which I've shown you before. And what's the concurrent history going to look like? Well, it's a sequence of events. So the first thing that happens is an invocation of the enqueue, and then the next thing is a deque by thread R, and then the enqueue is invoked by thread Q, and so forth. Yeah, the events with hats on them, they're the return events. So if I could point, I'll point on this one. So that's the sort of return event for the first enqueue. Okay. Right, the mapping function is basically going to be from indices to indices. So we're going to map, we're basically trying to capture this picture in some way, and the mapping function is mapping the index 0 to index 4, index 1 to index 0, and so forth. Yeah? And if we apply that mapping function, we'll end up with a sequential history that looks like that. Yeah, hope that's clear. Okay, so in terms of when we're defining correctness conditions, we only need the concurrent history and the mapping function. So we can actually determine what the corresponding sequential history is from a concurrent history and the mapping function. And I'm just going to use this predicate map, which returns the corresponding sequential history. Okay. We can also define validity of mapping functions. I won't give you the definition of that. And we can distinguish between these things called order and commitment. So order says that how must the order of events in the concurrent history be preserved by F, and commitment says that when must an event in the concurrent history be mapped by F. Yeah. But I'll go through examples of all this to make this clearer. Okay, so a correctness condition now basically is going to be a predicate of this form, where it's a conjunction of a number of order conditions and a number of commitment conditions. Okay. Now, of course, the goal was to define things that relate to concurrent objects. So we want to lift these history-level definitions to concurrent objects. And the way you do that is fairly, basically as you'd expect. Yeah? So we say a concurrent object C that implements an abstract object A is correct with respect to a correctness condition R, if and only if for any history of the object C, there exists some mapping function F such that the correctness condition holds, and also that when you construct the sequential history using this map function, then you get a history of the abstract object. Yeah, it's fairly clear, I think. Now, I'll just introduce some notation, this turnstile notation, which says, it's basically a notation for that definition. It says that C implementing A is correct with respect to R. Yes?
You say there exists a valid mapping function. Could it not be that there is a valid mapping function, but there's lots of other ones that don't satisfy these conditions?
Yes.
Would you want to say that for all valid mapping functions, those conditions fail?
No. You just need to find one. So, for example, linearizability. Let me go back to this picture. So there are other mapping functions. For example, I could linearize this x over there, and that would form another valid mapping function. But the sequential history that I get would be incorrect. Yeah. So you just need to find a linearization of the concurrent history. Yeah. Okay. Yeah. Okay. So there are some other technical details about incomplete histories and history extensions that are in the paper, but I'll let you read that or come and ask me later. Okay, so now we've got some formal basis. Let's formalize some correctness conditions. So first of all, linearizability, sequential consistency, and quiescent consistency, which are some of the more well-known ones. Yeah. So for each of these, it turns out that we've got this property that when an operation call returns, the operation call must also have taken effect. Yeah? So operation call returned implies operation call has taken effect. So what we'll do is capture this using a predicate, and we'll call this predicate total. And it just says that basically what I've said in the line above in English, and it's a formula that says for everything in the concurrent history H, if an event has returned, then that index must be in the mapping function. Yeah, so it must be mapped up to some sequential history, some sequential operation. Okay? So that's the common thing between, going back, common thing between linearizability, sequential consistency, and quiescent consistency. What's different? Well, the order conditions are different. Linearizability says that non-overlapping operation calls must not be reordered. Yeah. So looking at it, here's what a picture of that looks like. So you're not allowed to reorder the green and red operation calls because they don't overlap. But you could put the blue before or after, depending on whatever works. Yeah. So to capture that ordering condition, it's fairly straightforward. I just say that if I have mapped it up in this mapping function F, and M precedes, the index M precedes the index N. M is a return, N is an invocation, then at the sequential level, that orderer is preserved. Yeah, so it's fairly straightforward. Then we can lift this to objects themselves. So I say that, you can sort of read what's on the screen, but the correctness condition now becomes lin, where lin is little lin and total. So it's got an order condition lin and a commitment condition total. Okay, now looking at sequential consistency, it says operation calls by the same process must not be reordered, and here's what it looks like. So you can't reorder any of the red operation calls, but even if the blue one doesn't overlap with the red, you can actually, because they're in different threads, you can put that first if you need to. Okay, and it's fairly straightforward to define a predicate that captures this as well, and you get a similar lifting to history. Yes? What if those?
So what if P synchronizes with Q after its operation?
The correctness condition doesn't have anything to do with synchronization. It basically gives you restrictions on when you can reorder operation calls. Yeah. Okay, so Quiescent consistency is another correctness condition, and it says that operation calls separated by a quiescent point must not be reordered. Here's a picture of this. The yellow bars are the bits where things are quiescent. So quiescent means that nothing's executing. Yeah. And it's a fairly weak condition, and it says, as long as you're between two quiescent points, you can reorder in any way you like. Yeah? So the blues could be reordered in any way we like. The reds could be reordered in any way we like, but we can't reorder the red and the blue. And it's fairly easy to define this as well. You define what a quiescent point means. I won't go through the details. And then you basically say that if you have a quiescent point between two indices, then the order must be preserved at the sequential level. Okay? And then we lift to objects as per normal. Okay, so once we've done this, you can sort of develop part of the hierarchy where we can prove that linearizability implies sequential consistency, and that linearizability implies quiescent consistency as well. Yeah? Okay, so I'm going to now move on to multi-core architectures where we've had a talk already about some of the reorderings that can happen. This is an abstraction of an architecture where you use a local buffer before you write to shared memory. Okay, so write instructions may be pending in the local buffer before it goes to shared memory. I still find this surprising, which is why I've got 3 exclamation points there. And it says that instructions can take effect out of order. And this is the sort of standard. So we're looking at just TSO at this point, and this is the sort of standard TSO memory litmus test. So the post condition, if you execute this under totally ordered memory, meaning no weak memory effects, then you'll get that either R is equal to 1 or S is equal to 1. But if you execute this under TSO, then you can potentially have this, this third disjunct where R and S both capture the initial values of X and Y. And we know that we can prohibit reorderings by introducing fence instructions in the program code. Yeah? So I need to introduce those 2 fences so that the blue disjunct is disallowed. Okay? Now, fences are problematic because if you don't put enough in, then you get incorrect behaviors, and if you put too many in, then you end up with inefficient programs. Okay? But what about concurrent objects? Well, there's a paper in POPL 2011 by Attia et al., and they say that if you want to satisfy a strong condition like linearizability, then you're actually required to introduce fence instructions in the program code because you've got this strong correctness condition. So the question we're asking is, can we use fewer fences by adhering to some of the weaker conditions that we've seen already? Sequential consistency turns out to be a bit problematic because it's not compositional and it's not prefix closed. And quiescent consistency, as you saw before, was it is prefix closed and it is compositional, but it's a fairly weak condition. So we're trying to explore some other conditions for TSO that are sort of somehow weaker than linearizability, so you've got more possibilities for optimization, but somehow they give you better guarantees than just Quiescent consistency. Okay, so the case study we've got is this double-ended deque object, and it's used for load balancing in multiprocessor systems. So a deque is owned by a single worker process that can put and take tasks at the end of the queue, and it can be modified by multiple thief processes, which can steal tasks from the front of the queue, from the deque. Okay, and here's an abstract specification of this. I'm going to go through this fairly quickly because I'm running out of time. And here's a particular implementation by these people called Chase and Lev, where you've got an array-based, a shared array items, and a shared variable tail that keeps track of the end of the deque, and a shared variable head that keeps track of the start. Okay, I'm not going to ask you to try and understand that, but put the code up because I'm going to introduce some fences in a bit. Okay, so if you look at just totally ordered memory, so without any of the weak memory effects, then the Chase Lev deque is actually linearizable. Yeah. But if you run it under TSO, then you've got to introduce these two fences if you want to make this code linearizable. Okay, so the question we're asking is, can we do better? Well, if you remove the fence at T2 prime, then the whole thing is just nonsensical. Everything sort of breaks. But it's actually maybe possible to remove this fence at P3 prime, even though the program might no longer be linearizable. Okay? So the thing we sort of realize is that the effect of a put operation takes place when the tail, this shared tail variable is updated in shared memory, which means that the write at P3 is flushed. Yeah. So let me just sort of motivate this using some examples. Here's a non-linearizable history, and it's fairly easy to see why this is not linearizable, because you've got a put operation finishing, but somehow the steal. So we know that there's something in the deque, but somehow the steal is returning empty. Yeah? But what if we record some more information in the history? So for example, if we recorded that we could see the flush at P3 occurring, right? So we might end up with a history like this, and we can see that we can somehow work out that maybe the puts and the steals are actually overlapping somehow. Yeah? So if you sort of treat the flush of P3 as being the return of the put operation, then you can sort of transform the history into something like this. And now you can sort of see that the two operations overlap, and you can apply the standard sort of linearizability definition to the transformed history. Yeah. So that notion that I showed you is fairly simple, I think, conceptually, but the reasoning about these sorts of history transformations is fairly tricky. So the solution we've used is to somehow record all the writes and flush events in the history and use these mapping functions where you don't have totality. You've got these sort of partial commitments, which means that an operation call returning doesn't necessarily mean that the operation call has taken effect. Okay, so let me just sort of run through an example. Here's the same history again. Now, if we record all the writes and flushes, then we might see something like this. And it's fairly easy to see now where the corresponding flush for the corresponding write occurs. So the first flush is for the first write, second flush for the second write, and so forth, right? And then we might see the flush occurring at the end, and we'll say, well, how about this condition that allows you to reorder a put with any operation that is invoked before this index 9 being the very last flush that occurred. Okay, so then we end up with sort of this weak notion of weak ordering condition where you're allowed, I won't go through the whole thing, but you can reorder until the appropriate flush has occurred. And the commitment conditions say that, well, again, you've got this weak, it's not a total condition anymore, it's weak one where just because you've returned doesn't mean you have to take effect. Yeah. Then you can sort of define weakly flush consistent as being something that looks like this. I'll let you read the paper for all the details. Finally, that definition doesn't ensure sequential consistency, and sequential consistency is needed for this thing called observational refinement. But it's actually quite easy to develop the sequentially consistent variation just by adding it as a conjunct to the condition we've developed so far. Okay, so then we prove that this definition, this program we had before is flush consistent, where we got away with just one of the fences. So we didn't need two different fences. Okay, so wrapping it up, then there's this other notion of correctness called weak, I think Xi quiescent consistency, which is a variation on quiescent consistency, but for TSO. You can formalize that as well. And then we sort of use this formalization to develop a correctness hierarchy. And doing so, we actually ended up discovering a new condition called fence consistency, which we showed was non-blocking and compositional. So let me just show you the development of this hierarchy. So this is the one we already had for the total ones, which is that linearizability implies sequential consistency, and that linearizability implies quiescent consistency. Those are the total commit ones. So partial commitment, we end up with another little diagram like so. And so, we've got variations because we're still sort of trying to work out what all these things mean, so that there's lots of conditions being developed. Noticed a little gap there that sort of fits between, so we sort of filled in that gap. Then there's the question about how total commitment relates to partial commitment. And, well, you can actually draw an arrow from linearizability to this condition called flush consistency. But that's not all. We can also sort of go back and bring in some additional constraints on the histories to go from the partial commitment ones over to the total commitment conditions. Okay, so that's basically it. Yeah, so that paper is cited in this. So. They have several variations. So one of the variations has buffers in the abstract level.
So to know if something is linearizable or not, you don't need to speak about buffers.
I can't hear the question. I don't know if anyone else can, but I can't.
Is this on or? So in as far as I can remember, maybe I'm wrong, I don't think you need to reason about the actual contents of a buffer when you're proving linearizability in any of these other definitions. So the bottom line is that what's important is whether there has been a happens before relation between two operations that happen in different threads. Because if there has been a happens before relation, if there's been actual communication, you cannot reorder them, right? Like the effects of one operation have been made visible to the other. So that's, and you don't need to talk about fences or buffers or any of these things if you want.
For linearizability.
To define the property. You need to talk about it for the proofs, for sure. But so a little bit confused.
Yeah, well, maybe we can talk about that later. Yeah, it's a complicated question, I think. Yeah.